Picture this: a force so powerful it can bend light, devour stars, and warp the very fabric of time and space. Hidden at the heart of almost every galaxy lies a monster, a supermassive black hole, millions to billions of times heavier than our Sun. Think of them as the universe's ultimate vacuum cleaners, pulling in everything that dares to wander too close. Yet, these cosmic giants are more than just destructive forces. They are the architects of galaxies, shaping the universe as we know it. Today, we're diving into the mysterious world of supermassive black holes, uncovering 50 secrets that will leave you in awe of their power and complexity. From their mind-bending physics to their role in the birth and death of galaxies, this journey will challenge everything you thought you knew about the cosmos. Strap in, because by the end of this video, you'll see the universe in a whole new light. Let's begin. Moving into the first secret, let's uncover how these colossal cosmic giants come into existence. The formation of supermassive black holes is one of the most intriguing puzzles in astrophysics. Scientists have proposed several theories, and one of the leading ideas is direct collapse. In this scenario, massive clouds of gas collapse under their own gravity, bypassing the star formation stage entirely. This process could give birth to a black hole with a mass thousands of times greater than our Sun in just a short cosmic timescale. Another theory suggests that supermassive black holes grow from smaller ones, formed by the collapse of massive stars. Over time, these stellar black holes merge with others, growing larger and larger through a series of collisions and mergers. But that's not all. Accretion plays a crucial role too. As these black holes pull in gas, dust, and even stars from their surroundings, they consume this material, growing at an astonishing rate. It's like a cosmic snowball effect where they become more massive and more powerful with every bite. Together, these processes paint a picture of how supermassive black holes evolve from humble beginnings into the colossal structures that dominate the centers of galaxies. Next up, we'll explore how dark matter might be intertwined with these mysterious giants. Stay with us. Now, let's shift our focus to one of the most mysterious elements in the universe, dark matter, and its potential connection to supermassive black holes. While dark matter doesn't emit light or interact with electromagnetic forces, it exerts a powerful gravitational pull, shaping the structure of galaxies and the cosmos itself. Scientists have proposed that dark matter might play a crucial role in the formation and growth of supermassive black holes. Here's how. In the early universe, dark matter is thought to have formed vast halos, dense, invisible structures that acted as the scaffolding for galaxies. These dark matter halos drew in ordinary matter like gas and dust, creating the first seeds of galaxies. But could they also have nurtured the birth of supermassive black holes? Some theories suggest that dark matter halos provided the gravitational conditions necessary for direct collapse, allowing massive clouds of gas to form black holes without ever becoming stars. As these black holes grew, dark matter may have continued to feed them indirectly by pulling in more gas and material from their surroundings. Even more intriguing is the idea that dark matter itself could have been a direct source of mass. Some models propose that certain types of dark matter particles could accumulate at the centers of galaxies, eventually collapsing into black holes. While this remains a hypothesis, it opens up fascinating possibilities about the hidden forces shaping these cosmic giants. Together, dark matter and supermassive black holes might share a deep, invisible connection, working in tandem to build the massive structures we see at the heart of galaxies. Next, we'll dive into the event horizon, the point of no return where the rules of physics as we know them begin to break down. Stay tuned. Moving deeper into the mysteries of supermassive black holes, we now approach one of their most defining features, the event horizon. This invisible boundary marks the point where the gravitational pull becomes so intense that nothing, not even light, can escape. Picture it as the ultimate cosmic trapdoor. Once you cross this threshold, there's no turning back, no way to send a signal, and no chance of escape. Within the event horizon, the laws of physics as we know them cease to function normally. Time and space twist into something unrecognizable, and the fate of anything that crosses becomes sealed. Imagine a river flowing toward a waterfall. Just as the water accelerates and plunges over the edge, matter and light drawn toward a black hole accelerate as they approach the event horizon. At this point, the forces are so overwhelming that even light, the fastest thing in the universe, can't break free. It's as if the black hole is bending the fabric of reality itself. For an outside observer, an object falling toward the event horizon would appear to slow down and fade, eventually freezing in time at the boundary. Yet, for the object itself, the journey continues, spiraling inexorably toward the singularity at the center. This eerie phenomenon highlights the sheer power of supermassive black holes and the profound mysteries they hold. Next, we'll explore what happens to objects that venture too close, a process as bizarre as it is fascinating, known as spaghettification. Stay tuned. Now, let's dive into one of the most mind-bending phenomena tied to black holes, the process known as spaghettification. Imagine stepping toward a black hole, perhaps naively thinking you could resist its pull. As you get closer, the tidal forces, the difference in gravity between your head and your feet becomes so extreme that they stretch you out like a piece of spaghetti. This isn't science fiction, it's a real and inevitable fate for anything unlucky enough to venture too close. To put it into perspective, think of a rubber band. When you pull it from both ends, it elongates until it's thin and taut. Now amplify that force by billions of times and you've got spaghettification. The black hole's immense gravity stretches matter in one direction while compressing it in another, turning it into a long, thin strand. Even something as solid as a planet or a star wouldn't stand a chance. This process isn't just about stretching, though. As the object gets closer to the black hole, the tidal forces become so extreme that they tear it apart at the atomic level. It's as if the black hole is unraveling the very fabric of reality itself. For an observer watching from a safe distance, this would appear as a glowing stream of matter spiraling into the abyss, a stark reminder of the raw power these cosmic giants wield. Spaghettification is a vivid example of how black holes don't just pull things in, they utterly transform them, leaving nothing recognizable behind. Next, we'll explore how even black holes aren't entirely black as we uncover the fascinating concept of Hawking radiation. Stay with us now, shifting our focus to something truly revolutionary. Let's explore the concept of Hawking radiation. This groundbreaking idea, proposed by the legendary physicist Stephen Hawking, challenges the very notion that black holes are entirely black. Hawking suggested that black holes aren't just cosmic vacuum cleaners sucking in everything around them. They actually emit radiation, a phenomenon now known as Hawking radiation. Here's how it works. Near the edge of a black hole, pairs of particles and antiparticles constantly pop in and out of existence. Normally, these pairs annihilate each other instantly. But when this happens right at the event horizon, one particle can fall into the black hole while the other escapes into space. The escaping particle carries away energy, which over time causes the black hole to lose mass. This means black holes aren't eternal, they slowly evaporate. The smaller the black hole, the faster it evaporates. For a supermassive black hole, this process would take an unimaginably long time, trillions upon trillions of years. But for smaller black holes, it could happen much more quickly. Hawking's theory was a game-changer because it linked quantum mechanics and gravity, two fields of physics that had previously seemed incompatible. It also posed a profound question. What happens to all the information swallowed by the black hole when it eventually evaporates? This question, known as the black hole information paradox, remains one of the biggest mysteries in physics. Hawking radiation isn't just a theoretical curiosity, It's a key piece of the puzzle in understanding the life cycle of black holes and the fate of the universe itself. Up next, we'll uncover how supermassive black holes are deeply connected to the very galaxies they call home. Stay curious. Now, let's delve into a fascinating relationship that's as dynamic as it is mysterious: the bond between supermassive black holes and the galaxies they inhabit. These colossal objects aren't just passive residents at the center of galaxies. They play a vital role in shaping their cosmic neighborhoods. Think of it as a two-way street. Galaxies provide the fuel for supermassive black holes to grow, and in turn, these black holes influence the very structure and evolution of their host galaxies. One of the most striking ways they do this is through what's known as feedback. When a supermassive black hole feeds on surrounding matter, it doesn't just gobble it up quietly. It releases enormous amounts of energy in the form of radiation and powerful jets. This energy can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars. In some cases, this feedback can even blow gas out of the galaxy entirely, effectively putting a brake on star formation. But that's not all. Supermassive black holes also seem to be connected to the overall size and shape of their galaxies. Observations show that the more massive the black hole, the larger the galaxy's central bulge of stars. This suggests that the growth of a supermassive black hole and its galaxy are intertwined, likely through a series of cosmic events like mergers and collisions. When galaxies collide, their supermassive black holes can eventually merge, releasing gravitational waves and triggering bursts of star formation. It's a complex dance of destruction and creation, with supermassive black holes acting as both architects and regulators of their galactic homes. So, the next time you gaze at a galaxy, remember the supermassive black hole at its center isn't just a silent observer. It's a key player in the story of how galaxies are born, grow, and evolve. Up next, we'll explore how these black holes power some of the brightest objects in the universe, quasars. Stay with us. Now, let's turn our attention to one of the most luminous and enigmatic phenomena in the cosmos: quasars. These dazzling objects are the brightest beacons in the universe, outshining entire galaxies. But what makes them so incredibly bright? The answer lies in the supermassive black holes at their cores. Quasars are powered by the immense energy released as matter spirals into these black holes at nearly the speed of light, forming what's known as an accretion disk. As this material heats up, it emits staggering amounts of light and radiation, making quasars visible across billions of light years. Not only are quasars a spectacle of cosmic brightness, but they also serve as invaluable tools for scientists studying the early universe. Because quasars are so luminous, they can be observed from vast distances, effectively giving us a window into the universe's past. The light from the most distant quasars has traveled for billions of years, allowing astronomers to study the conditions of the universe when it was just a fraction of its current age. Through quasars, we've learned about the chemical composition of the early cosmos, the formation of the first galaxies, and even the distribution of matter in the universe. Interestingly, quasars also provide clues about the evolution of supermassive black holes themselves. The fact that we see quasars in the early universe suggests that supermassive black holes grew to enormous sizes remarkably quickly. This raises intriguing questions about how these black holes formed and how they accumulated so much mass in such a short time. So, while quasars are a breathtaking cosmic phenomenon in their own right, they're also a critical piece of the puzzle in our quest to understand the universe's origins and evolution. Next, we'll explore another incredible feature of supermassive black holes: the powerful jets of particles they launch into space. Don't go anywhere. Moving from the brilliance of quasars, let's dive into another astonishing phenomenon tied to supermassive black holes: the jets of relativistic particles they unleash into the cosmos. These jets are among the most energetic features in the universe, shooting out from the poles of supermassive black holes at speeds approaching that of light. But what exactly powers these jets, and what effects do they have on their surroundings? The process begins in the accretion disk, the swirling ring of matter that orbits the black hole. As material spirals inward, not all of it is consumed. Some of it gets funneled into powerful magnetic fields near the black hole's poles. These fields act like cosmic particle accelerators, launching streams of charged particles, mostly electrons and protons, outward at incredible speeds. These jets can stretch for thousands, even millions of light years, far beyond the boundaries of their host galaxies. The impact of these jets is profound. When they collide with the surrounding interstellar medium, they can trigger shock waves, heating the gas and preventing it from collapsing to form stars. In some cases, this process can effectively shut down star formation in entire regions of a galaxy. On the other hand, these jets can also compress nearby gas clouds, triggering bursts of star formation in other areas. This dual role makes them a key player in shaping the evolution of their host galaxies. But the influence of these jets extends even further. They can also seed the intergalactic medium with heavy elements, enriching the space between galaxies with the building blocks of future stars and planets. Additionally, the high-energy particles in these jets can produce gamma rays and other forms of radiation, making them detectable across vast cosmic distances. These jets are not just a byproduct of supermassive black holes, they're a testament to the immense energy these cosmic giants wield. By studying them, scientists gain insights into the behavior of black holes, the structure of galaxies, and the dynamics of the universe itself. Up next, we'll take a closer look at the supermassive black hole at the heart of our own galaxy, Sagittarius A star. Stay tuned. Now, let's turn our gaze closer to home, to the supermassive black hole that lies at the heart of our own galaxy, Sagittarius A star. Discovered in the 1970s, Sagittarius A star has since become one of the most studied objects in the universe. Unlike its more distant and active counterparts, Sagittarius A star is relatively quiet, but its calm exterior hides a gravitational powerhouse with a mass of about 4 million times that of our Sun. What makes Sagittarius A star so fascinating is its unique position in the Milky Way. Located roughly 26,000 light-years from Earth, it's close enough for detailed observation, yet far enough to remain mysterious. Scientists first detected it through radio waves emitted by hot gas swirling around its event horizon. Over time, advancements in technology, such as the Event Horizon Telescope, have allowed us to capture unprecedented images of its shadow, revealing the intense gravitational forces at work. Despite its immense power, Sagittarius A star is surprisingly inactive compared to other supermassive black holes. This quiet nature has puzzled astronomers. One theory suggests that it's in a phase of low accretion, meaning it's not consuming large amounts of matter at the moment. However, there are signs of occasional activity, such as flares that erupt when stray gas or dust falls into its grasp. These flares provide valuable clues about the environment near the event horizon. Another intriguing aspect of Sagittarius A star is its influence on the stars orbiting around it. Some stars whip around the black hole at astonishing speeds, completing their orbits in just a few years. By studying these stars, scientists can map the gravitational field of Sagittarius A star and test predictions made by Einstein's theory of general relativity. Sagittarius A star serves as a cosmic laboratory, offering us a front-row seat to study the behavior of supermassive black holes. Its relative proximity makes it a key to unlocking many of the secrets about these enigmatic objects, from their role in galaxy formation to the nature of spacetime itself. Next, we'll venture farther into the cosmos to meet the largest black hole ever discovered. Stay with us. Now, let's journey to the far reaches of the cosmos to meet the largest black hole ever discovered, Ton 618. This colossal giant is unlike anything we've encountered before, with a mass so immense it defies comprehension. Ton 618 is estimated to weigh in at a staggering 66 billion times the mass of our Sun, making it one of the most massive objects in the known universe. What sets TON 618 apart is not just its size but also its incredible luminosity. It's classified as a quasar, meaning it's fueled by the supermassive black hole at its core, which gobbles up matter at an extraordinary rate. As matter spirals into the black hole, it heats up and emits an intense glow, outshining entire galaxies. In fact, TON 618 is so bright that it was first detected in the 1950s as a faint point of light, long before its true nature was understood. The sheer scale of TON 618 is almost impossible to grasp. Its event horizon, the point of no return, stretches across a distance that could engulf our entire solar system many times over. To put it in perspective, if you were to travel at the speed of light, it would take you weeks to cross from one side of TON 618 event horizon to the other. But what's even more fascinating is how TON 618 challenges our understanding of black hole formation. Scientists are still trying to piece together how such a behemoth could have formed in the early universe. Some theories suggest it grew through a combination of rapid accretion and mergers with other massive black holes, but the exact process remains a mystery. TON 618 also provides a glimpse into the extremes of the universe. Its immense gravitational pull warps spacetime to an extraordinary degree, creating an environment where the laws of physics as we know them begin to break down. Studying TON 618 helps scientists test the limits of our current theories and explore the nature of spacetime itself. As we marvel at the enormity of TON 618, it's worth remembering that black holes like this are not just cosmic curiosities, they're windows into the fundamental workings of the universe. Next, we'll explore another intriguing aspect of supermassive black holes, how they spin and why it matters. Stay tuned. Now, let's turn our attention to another fascinating feature of supermassive black holes, their spin. Just like planets and stars, these cosmic giants rotate, and their spin plays a crucial role in shaping their behavior and the energy they release. The spin of a supermassive black hole is determined by the angular momentum of the matter it consumes. As material spirals into the black hole, it transfers its rotational energy, causing the black hole itself to spin faster. This rotation can reach incredible speeds, sometimes approaching the maximum limit allowed by the laws of physics. But why does spin matter? For one, it influences the structure of the black hole's accretion disk, the swirling ring of matter that surrounds it. A rapidly spinning black hole can warp the inner regions of this disk, creating a more dynamic and energetic environment. This, in turn, can lead to the release of enormous amounts of energy in the form of radiation and jets of particles, which can stretch across millions of light years. The spin of a black hole also affects its gravitational pull and the way it warps spacetime. A spinning black hole drags spacetime around with it, a phenomenon known as frame dragging. This effect can create what's called an ergosphere, a region outside the event horizon where particles and even light can be forced to move in the same direction as the black hole's spin. Understanding the spin of supermassive black holes helps scientists unravel their formation and evolution. For example, a black hole with a high spin might have grown primarily through accretion, while one with a slower spin could have formed through mergers with other black holes. Studying black hole spin also provides insights into the extreme physics of these objects. It helps test theories like general relativity and sheds light on how black holes influence their surroundings, from shaping galaxies to powering quasars. As we delve deeper into the mysteries of supermassive black holes, their spin reminds us that these cosmic giants are not just static objects, they are dynamic, spinning powerhouses that shape the universe in profound ways. Next, we'll explore the swirling ring of matter known as the accretion disk and how it transforms the environment around a black hole. Stay with us. Now that we've explored the spin of supermassive black holes, let's take a closer look at one of the most dramatic features surrounding them, the accretion disk. This swirling ring of matter is not just a passive bystander. It's a powerhouse of energy and activity that shapes the behavior of the black hole itself. The accretion disk forms as material, gas, dust, and even stars gets pulled toward the black hole by its immense gravitational force. Instead of falling straight in, this matter spirals inward, much like water circling a drain. As it does, it heats up to extreme temperatures, reaching millions of degrees. This heat causes the disk to glow brightly, emitting radiation across the electromagnetic spectrum, from radio waves to X-rays. The inner regions of the accretion disk closest to the black hole are the most energetic. Here, friction and turbulence among the particles generate tremendous amounts of heat and light. This energy is so intense that it can outshine entire galaxies, making the accretion disk one of the brightest objects in the universe when viewed from afar. But the accretion disk isn't just a source of light, it's also a key player in feeding the black hole. As matter spirals inward, it loses energy and eventually crosses the event horizon, adding to the black hole's mass. At the same time, some of the material is ejected outward in powerful jets, propelled by magnetic fields and the black hole's spin. These jets can stretch across vast distances, influencing the surrounding galaxy and even intergalactic space. Interestingly, the structure of the accretion disk depends heavily on the black hole's spin. A rapidly spinning black hole can warp the inner regions of the disk, creating a more complex and dynamic environment. This warping can also affect the amount of energy released, making some black holes even more luminous than others. Understanding accretion disks helps scientists unlock the mysteries of how black holes grow and interact with their surroundings. These disks are not just cosmic decorations, they are dynamic systems that drive the evolution of galaxies and provide critical insights into the extreme physics of black holes. As we continue our journey, we'll dive into another mind-bending concept, time dilation near black holes, and explore how these cosmic giants warp the very fabric of time. Stay tuned. Now, let's shift our focus to one of the most mind-bending effects of supermassive black holes, time dilation. This phenomenon, predicted by Einstein's theory of general relativity, reveals how gravity can warp the very fabric of time itself. Near a supermassive black hole where gravity is unimaginably strong, time doesn't just slow down, it crawls. To understand this, imagine two astronauts. One stays far away from the black hole, while the other ventures close to the event horizon. For the distant astronaut, time passes as usual, but for the one near the black hole, time slows dramatically. If they could communicate, the distant astronaut would hear the other's messages coming slower and slower, as if time itself was stretching out. This effect becomes even more extreme the closer you get to the black hole. At the event horizon, time effectively stops from the perspective of an outside observer. An object falling toward the black hole would appear to freeze in place, never quite crossing the horizon, even though from the object's own perspective, it would pass through in an instant. Let's take this a step further with a thought experiment. Picture a clock hovering near a supermassive black hole and another clock far away in space. If you could watch both clocks simultaneously, you'd see the one near the black hole ticking slower and slower compared to the distant one. This isn't just an illusion, it's a real effect caused by the intense gravitational field warping spacetime. Time dilation isn't just a theoretical curiosity, it has real-world implications. For instance, if a spacecraft were to orbit close to a supermassive black hole, the crew would age more slowly than people on Earth. While this sounds like science fiction, it's grounded in the laws of physics and helps scientists test and refine our understanding of gravity. This concept also challenges our intuitive sense of time. Time, which we often think of as constant and universal, is actually fluid and relative. Near a supermassive black hole, the extreme conditions reveal just how much gravity can influence the passage of time. As we continue, we'll explore another groundbreaking discovery, the detection of gravitational waves from merging black holes, and uncover what these ripples in spacetime tell us about the universe. Stay with us as we dive deeper into the mysteries of these cosmic giants. Now, let's turn our attention to one of the most thrilling discoveries in modern astrophysics: gravitational waves. These ripples in spacetime, first predicted by Einstein over a century ago, were finally detected in 2015, opening up an entirely new way to observe the universe. Gravitational waves are created when massive objects like supermassive black holes collide and merge. The sheer power of such an event sends shockwaves through the fabric of spacetime itself, much like tossing a stone into a pond creates ripples. These waves travel outward at the speed of light, carrying with them information about the objects that created them. The detection of these waves was a monumental achievement. Using incredibly sensitive instruments called laser interferometers, scientists were able to measure the tiny distortions in spacetime caused by a pair of merging black holes. The first event, detected by the LIGO Observatory, involved two black holes spiraling into each other over 1 billion light-years away. The collision unleashed energy equivalent to several times the mass of the Sun, all in the form of gravitational waves. So, what do these waves tell us? For starters, they provide direct evidence of black hole mergers, something that had only been theorized before. They also give us insights into the properties of black holes, such as their masses and spins. By studying the waveforms, the unique patterns of the ripples, scientists can piece together the story of the merger, from the initial spiraling to the final collision and the resulting single, more massive black hole. But the implications go even deeper. Gravitational waves allow us to probe regions of the universe that are otherwise invisible. Light, for example, can be blocked by dust or absorbed by gas, but gravitational waves pass through everything unaffected. This means we can now listen to the universe in a way we never could before, revealing hidden phenomena like the mergers of supermassive black holes in distant galaxies. These waves also help us test Einstein's theory of general relativity in extreme conditions. So far, every detection has matched the predictions of relativity, reinforcing our understanding of gravity. But there's always the possibility that future observations could reveal something unexpected, potentially leading to new physics. As we continue our journey through the secrets of supermassive black holes, we'll explore another cosmic mystery: the black hole information paradox. This puzzle challenges our understanding of the universe at its most fundamental level. Stay with us as we unravel this profound enigma. Now, let's venture into one of the most perplexing mysteries in the realm of physics: the black hole information paradox. This puzzle strikes at the very heart of our understanding of the universe, challenging two of the most successful theories ever devised: quantum mechanics and Einstein's theory of general relativity. At its core, the paradox arises from a simple question: what happens to information when it falls into a black hole? According to quantum mechanics, information in the universe can never truly be destroyed. It might change forms, but it always persists. However, black holes seem to defy this rule. When matter falls into a black hole, it's thought to be lost forever, crushed into the singularity at the center. This creates a conflict. Where does the information go? Einstein's theory of general relativity adds another layer to the mystery. It describes black holes as objects with an event horizon, a boundary beyond which nothing, not even light, can escape. Once something crosses this horizon, it's gone from our observable universe. From this perspective, information appears to vanish, which contradicts the principles of quantum mechanics. This paradox has puzzled physicists for decades, leading to a variety of theories and speculations. One intriguing idea is that information isn't truly lost but is instead encoded in some way on the event horizon. This concept, known as the holographic principle, suggests that all the information about what falls into a black hole could be stored in a two-dimensional surface on the horizon, like a cosmic hard drive. Another possibility is that information escapes back into the universe through Hawking radiation, the process by which black holes slowly lose mass and energy. While this radiation was originally thought to be random and devoid of information, some physicists now believe it might carry encoded details about the matter that fell into the black hole. The implications of resolving this paradox are profound. It could lead to a deeper understanding of how gravity and quantum mechanics intersect, potentially paving the way for a unified theory of everything. It might also reshape our understanding of the nature of reality itself, challenging long-held assumptions about space, time, and information. As we continue to probe this enigma, the black hole information paradox reminds us just how much we have yet to learn about the universe. Next, we'll explore another fascinating aspect of black holes, the existence of intermediate mass black holes, which may hold clues to the missing links in our cosmic understanding. Moving forward, let's turn our attention to a fascinating yet elusive category of cosmic objects: intermediate mass black holes. These mysterious entities could be the missing link that bridges the gap between stellar black holes, formed from collapsing stars, and the colossal supermassive black holes that dominate galactic centers. While stellar black holes typically weigh in at a few times the mass of our Sun, and supermassive black holes can be millions or even billions of times heavier, intermediate mass black holes occupy a middle ground ranging from hundreds to tens of thousands of solar masses. So, why are these intermediate mass black holes so important? For one, their existence could help us understand how supermassive black holes grow to such immense sizes. Scientists have long theorized that smaller black holes merge over time, gradually accumulating mass. Intermediate mass black holes could be a critical step in this process, acting as the building blocks that eventually form their supermassive counterparts. But detecting these mid-sized black holes has proven to be a significant challenge. Unlike stellar black holes, which can be identified through their interactions with nearby stars, or supermassive black holes, which are unmistakable due to their powerful influence on entire galaxies, intermediate mass black holes are harder to spot. They often reside in less dense regions, such as globular clusters, where their presence is subtle and their effects are harder to observe. One promising clue comes from gravitational waves, ripples in space-time caused by violent cosmic events. In recent years, detectors like LIGO and Virgo have picked up signals that could point to the collisions of intermediate mass black holes. These observations provide tantalizing evidence that these objects do exist, even if they remain shrouded in mystery. Another intriguing possibility is that intermediate mass black holes could be the remnants of the universe's first stars, known as population 3 stars. These ancient giants, which formed shortly after the Big Bang, could have collapsed directly into black holes of intermediate size, offering a glimpse into the early stages of cosmic evolution. Understanding these black holes isn't just about filling a gap in our knowledge, it's about piecing together the story of how black holes, and by extension galaxies, form and evolve. Intermediate mass black holes could be the key to unlocking some of the universe's most profound secrets, from the origins of supermassive black holes to the dynamics of cosmic growth. As we continue to search for and study these enigmatic objects, one thing is clear: they hold the potential to reshape our understanding of the cosmos. Next, we'll dive into another captivating topic: the theoretical connection between black holes and wormholes, and how they might serve as shortcuts through spacetime. Now, let's venture into the realm of one of the most intriguing theoretical concepts in astrophysics: the connection between black holes and wormholes. Imagine a shortcut through the fabric of spacetime, a cosmic tunnel that could instantly connect distant parts of the universe. This is the idea behind wormholes, and black holes might just hold the key to their existence. In theory, a wormhole is a bridge between two separate points in spacetime, effectively creating a shortcut that could allow matter or even information to travel vast distances in an instant. While wormholes are purely hypothetical at this stage, some scientists believe that black holes could be the entrance points to these tunnels. the intense gravitational pull of a black hole might create the conditions necessary for a wormhole to form, bending space-time so drastically that it folds in on itself. Einstein's theory of general relativity actually allows for the possibility of wormholes, though they would require exotic matter with negative energy to remain stable. This exotic matter would counteract the immense gravitational forces trying to collapse the wormhole, keeping it open long enough for anything to pass through. The challenge, of course, is that such matter has never been observed, leaving wormholes in the realm of speculation. One fascinating aspect of this idea is that wormholes could potentially allow for faster-than-light travel, bypassing the limitations imposed by the speed of light. While this sounds like science fiction, it's grounded in the mathematics of relativity. If a wormhole were stable and traversable, it could serve as a cosmic shortcut, revolutionizing our understanding of space travel and the structure of the universe. But there's a catch. Even if wormholes exist, they would likely be incredibly unstable, collapsing almost instantly under the pressure of their own gravity. Additionally, the intense tidal forces near a black hole, the same forces that cause spaghettification, would make traveling through a wormhole extremely perilous, if not impossible. This has led some scientists to propose that wormholes might only be useful for microscopic particles or quantum information, rather than for human-scale travel. Despite these challenges, the idea of black holes as gateways to wormholes continues to captivate both scientists and the public. It's a reminder of how much we still have to learn about the universe and the strange phenomena that might exist within it. While wormholes remain theoretical, they serve as a powerful symbol of the boundless possibilities that await us in the exploration of space and time. Up next, we'll explore another fascinating principle in black hole physics, the no-hair theorem, which simplifies these cosmic giants into just 3 defining characteristics. Stay tuned as we unravel more secrets of these enigmatic objects. Shifting our focus to another fascinating aspect of black hole physics, let's delve into the no-hair theorem. This principle, rooted in Einstein's theory of general relativity, suggests that black holes are remarkably simple objects despite their immense complexity. According to the theorem, a black hole can be completely described by just 3 properties: its mass, its electric charge, and its spin. That's it, no other details matter. This idea is often summarized by saying that black holes have no hair, meaning they lack any additional distinguishing features. At first glance, this might seem counterintuitive. Black holes are formed from the collapse of massive stars, which can have a wide variety of properties such as composition, structure, and magnetic fields. Yet, once a black hole forms, all of this information appears to be lost, leaving behind only these 3 fundamental characteristics. This is why the no-hair theorem is sometimes referred to as the baldness of black holes. The implications of this principle are profound. It means that, in a sense, black holes erase the complexity of the matter that fell into them, leaving behind a clean slate defined by mass, charge, and spin. This simplicity is both elegant and puzzling, as it raises questions about what happens to all the other information that seems to vanish once it crosses the event horizon. This ties into the black hole information paradox, a major unresolved issue in physics. Interestingly, the no-hair theorem also suggests that black holes are somewhat like cosmic fingerprints. No 2 black holes can be exactly alike unless they share the same mass, charge, and spin. This makes them unique in the universe, even as it simplifies their description. For scientists, this theorem provides a powerful tool for studying black holes, as it reduces their behavior to just these 3 parameters. However, the no-hair theorem isn't without its challenges. Some theories, particularly in the realm of quantum mechanics, suggest that black holes might have more hair than we currently understand. For instance, quantum effects could introduce subtle differences that aren't captured by the classical description of black holes. This remains an area of active research, as scientists work to reconcile the no-hair theorem with the complexities of quantum physics. In essence, the no-hair theorem offers a strikingly simple way to understand black holes, reducing these cosmic giants to just 3 defining traits. Yet, it also highlights the profound mysteries that still surround them, reminding us of how much we have yet to uncover about the universe's most enigmatic objects. Next, we'll explore the singularity, the mysterious point at the center of a black hole where the laws of physics as we know them break down completely. Stay with us as we journey deeper into the heart of these cosmic wonders. At the core of every black hole lies a point of infinite mystery, the singularity. This is the very heart of a black hole, where gravity becomes so intense that it crushes matter into a region of zero volume and infinite density. Here, the laws of physics as we know them cease to function, and our understanding of the universe hits a wall. The singularity is without a doubt one of the most perplexing puzzles in modern science. To grasp just how bizarre this concept is, imagine squeezing an entire star or even an entire galaxy into a single point. That's essentially what happens at the singularity. The gravitational pull is so overwhelming that nothing, not even light, can escape its grasp. It's a place where space-time itself breaks down and the rules of classical physics no longer apply. One of the reasons the singularity is so mysterious is that it represents a breakdown in our current scientific models. Einstein's theory of general relativity predicts the existence of singularities, but it can't explain what happens inside them. At these extreme conditions, quantum effects, which govern the behavior of particles on the smallest scales, are thought to become dominant. However, we still lack a unified theory that combines general relativity and quantum mechanics, leaving the singularity shrouded in uncertainty. The singularity also challenges our understanding of the universe's fundamental nature. Is it truly a point of infinite density, or is it something else entirely? Some scientists speculate that new physics beyond our current knowledge might offer answers. For instance, theories like quantum gravity or string theory propose that singularities could be replaced by structures with finite size and density, offering a way to resolve the infinite nature predicted by classical physics. Adding to the intrigue is the fact that we can't directly observe the singularity. It's hidden behind the event horizon, the boundary beyond which nothing can escape. This means that all our knowledge about the singularity comes from theoretical models rather than direct evidence. It's a cosmic enigma that pushes the boundaries of our imagination and scientific understanding. In essence, the singularity is a reminder of how much we still have to learn about the universe. It's a place where the known meets the unknown, and where the frontiers of physics beckon us to explore further. Next, we'll turn our attention to black hole shadows, the eerie silhouettes that provide our first direct glimpse into the structure of these cosmic giants. Stay tuned as we uncover what these shadows reveal about the nature of black holes. Now, let's shift our gaze to one of the most groundbreaking achievements in astrophysics, the first ever image of a black hole's shadow. This historic moment occurred in April 2019, when the Event Horizon Telescope, a global network of radio telescopes, captured an image of the supermassive black hole at the center of the galaxy Messier 87. The image itself is a mesmerizing ring of light surrounding a dark central region, the shadow of the black hole. This shadow isn't the black hole itself, but rather the absence of light caused by the black hole's immense gravitational pull. Light from the surrounding accretion disk bends and is sucked into the black hole, creating this eerie silhouette. What makes this image so significant is that it provides the first direct visual evidence of a black hole structure. It confirms predictions made by Einstein's theory of general relativity, particularly how space-time is warped in the presence of such extreme gravity. The size and shape of the shadow align closely with theoretical models, giving scientists confidence in our understanding of these cosmic behemoths. The Event Horizon Telescope achieved this feat by combining data from multiple telescopes across the globe, effectively creating a virtual telescope the size of Earth. This allowed it to capture details at an unprecedented resolution, revealing features just 37 microarcseconds across, a scale equivalent to spotting an orange on the surface of the Moon from Earth. Beyond confirming theory, the image has opened new avenues for research. It provides insights into the behavior of matter and energy near the event horizon, the boundary beyond which nothing can escape. By studying the light around the shadow, scientists can learn more about how black holes consume matter, power jets of particles, and influence their surroundings. The image of the black hole shadow also raises intriguing questions. For instance, why does the ring of light appear brighter on one side? This asymmetry is likely due to the Doppler effect, where light is intensified as it moves toward us and dimmed as it moves away, hinting at the black hole's rotation. In essence, this first ever image of a black hole's shadow is more than just a stunning photograph. It's a window into the heart of one of the universe's most mysterious objects. It marks a turning point in our ability to observe and understand black holes, bringing us one step closer to unraveling their secrets. Next, we'll explore the role of magnetic fields in shaping the behavior of supermassive black holes and their surrounding environments. Stay with us as we delve into this fascinating aspect of these cosmic giants. Now, let's turn our attention to another critical force shaping the behavior of supermassive black holes: magnetic fields. While gravity dominates the conversation around these cosmic giants, magnetic fields play a surprisingly vital role in their dynamics, particularly within their accretion disks. Magnetic fields are generated by the swirling motion of charged particles in the accretion disk, the superheated ring of matter orbiting a black hole. These fields are not just passive bystanders, they actively influence how matter behaves as it spirals inward. For instance, magnetic fields can cause turbulence within the disk, which affects how quickly matter is funneled into the black hole. This turbulence can also lead to the formation of powerful jets of particles, launching them outward at nearly the speed of light. But how do these jets form? Magnetic fields act like cosmic slingshots, channeling energy from the accretion disk and accelerating charged particles along the black hole's rotational axis. These jets can stretch for thousands of light years, carving through interstellar space and impacting entire galaxies. They are so energetic that they can heat up surrounding gas, preventing it from collapsing into stars, and even halt star formation in their host galaxies. Magnetic fields also play a role in regulating the black hole's diet. They can create resistance, slowing down the flow of matter into the black hole, which affects how quickly it grows. In some cases, magnetic fields can even push material away, preventing it from being consumed altogether. This delicate balance between inflow and outflow is crucial for understanding how supermassive black holes evolve over time. Interestingly, magnetic fields might also explain why some black holes appear to flicker. Observations have shown that the brightness of certain accretion disks fluctuates rapidly. Scientists believe these changes could be caused by magnetic fields twisting and reconnecting, releasing bursts of energy in the process. In essence, magnetic fields are more than just a supporting player in the drama of supermassive black holes. They are a key architect of their behavior. They shape how matter moves, how energy is released, and even how black holes interact with their galactic surroundings. As we continue our journey, we'll explore the rare phenomenon of binary supermassive black holes and the extraordinary events that unfold when these cosmic giants collide. Now, let's shift our gaze to one of the rarest and most fascinating phenomena in the cosmos: binary supermassive black holes. These are systems where not one, but two supermassive black holes orbit each other, locked in a cosmic dance that can last for millions of years. But how do such systems come to exist in the first place? Binary supermassive black holes typically form when two galaxies collide and merge. Each galaxy likely harbors its own supermassive black hole at its center. As the galaxies combine, their black holes are drawn together by gravity, eventually forming a binary pair. At first, these black holes may orbit each other at vast distances, but over time they spiral closer as they lose energy through interactions with stars, gas, and other matter in their vicinity. As the black holes inch closer, their gravitational influence becomes increasingly intertwined. They begin to emit gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity. These waves carry away energy, causing the black holes to gradually lose their orbital distance. This process can take millions or even billions of years, but eventually, the black holes reach a point where they are just a fraction of a light year apart. The final act of this cosmic drama is the merger itself. When the black holes get close enough, they collide and combine into a single, even more massive black hole. This event releases an enormous amount of energy, not just in the form of gravitational waves, but also as bursts of light and radiation. The resulting gravitational waves are so powerful that they can be detected across vast distances, as was famously observed by the LIGO and Virgo collaborations for smaller black hole mergers. But what happens to the surrounding galaxy during this merger? The process can be incredibly disruptive. The gravitational forces involved can fling stars out of their orbits, alter the structure of the galaxy, and even trigger new waves of star formation. In some cases, the merger can also reignite the activity of the newly formed black hole, turning it into a bright quasar. The study of binary supermassive black holes offers a unique window into the evolution of galaxies and the behavior of these enigmatic objects. By observing these systems, scientists can learn more about the role of supermassive black holes in shaping the cosmos. As we continue our exploration, we'll delve into the intriguing idea that black holes might serve as gateways to other universes, a concept that pushes the boundaries of our understanding of spacetime itself. Now, let's venture into the realm of speculative science with the idea that black holes might serve as gateways to other universes. This concept stretches our understanding of spacetime and challenges the very fabric of physics as we know it. At the heart of this theory lies the idea that black holes, with their intense gravitational pull and ability to warp spacetime, could connect our universe to others. Some scientists propose that the singularity at the center of a black hole might not be a dead end but a bridge, a point where matter and energy could be funneled into a completely different universe. This concept is often referred to as a wormhole, a hypothetical tunnel through spacetime. The scientific basis for this idea comes from the equations of general relativity, which allow for the possibility of such structures. However, there's a catch. For a wormhole to be stable, it would require a form of exotic matter with negative energy to keep it open. This hypothetical substance defies the known laws of physics, making the existence of traversable wormholes highly speculative. Controversies abound in this field. Many physicists argue that while the math might allow for such phenomena, there's no observational evidence to support them. Others point out that even if wormholes exist, the extreme conditions at the center of a black hole would make traversing them impossible for anything or anyone that enters. Despite the controversies, the idea of black holes as gateways to other universes continues to captivate the imagination. It raises profound questions about the nature of reality and whether our universe is just one of many in a vast multiverse. While this remains a speculative theory, it pushes the boundaries of science and encourages us to think beyond the limits of our current knowledge. As we move forward, we'll explore how supermassive black holes might play a role in shaping the large-scale structure of the universe, a topic that brings us closer to understanding their true impact on the cosmos. Now, let's shift our focus to the cosmic web, a vast network that forms the backbone of the universe's large-scale structure. Supermassive black holes, it turns out, might play a crucial role in shaping this intricate framework. Picture the cosmic web as a tapestry of galaxies, gas, and dark matter, woven together by the forces of gravity. At the intersections of this web lie galaxy clusters, and at the heart of many of these clusters you'll find supermassive black holes. These colossal objects are not just passive residents, they actively influence their surroundings. As supermassive black holes consume matter, they release enormous amounts of energy in the form of jets and radiation. These emissions can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. This process, known as feedback, helps regulate the growth of galaxies and the structure of the cosmic web. But that's not all. The energy from supermassive black holes can also push gas out of galaxies, creating vast bubbles in the intergalactic medium. This redistributes matter across the cosmic web, influencing where new galaxies form and how the web evolves over time. In a way, supermassive black holes act like cosmic architects, shaping the universe on the largest scales. Interestingly, the relationship between supermassive black holes and the cosmic web is a two-way street. The web itself provides the raw material, gas and dark matter, that feeds these black holes, allowing them to grow and continue their work. This symbiotic relationship highlights the interconnected nature of the universe, where even the most massive structures are influenced by the smallest points of immense gravity. While much about this dynamic remains a mystery, ongoing observations and simulations are shedding light on how supermassive black holes contribute to the cosmic web. Understanding this role not only deepens our knowledge of black holes, but also helps us piece together the story of how the universe has evolved over billions of years. As we continue our journey, we'll explore another fascinating aspect of supermassive black holes, their role in the life cycles of galaxies, where their influence extends far beyond the cosmic web. Now, let's take a closer look at the life cycle of supermassive black holes, a journey that spans billions of years and reveals the incredible transformations these cosmic giants undergo. It all begins with their formation, a process that remains shrouded in mystery. One leading theory suggests that supermassive black holes could have formed from the direct collapse of massive gas clouds in the early universe, bypassing the stage of becoming stars entirely. Another possibility is that they grew from smaller black holes, merging repeatedly and accumulating mass over time. As these black holes grow, they enter a phase of intense activity. Feeding on surrounding gas, dust, and even entire stars, they power some of the brightest objects in the universe, such as quasars. During this stage, they release vast amounts of energy, influencing the evolution of their host galaxies. But this period of feasting isn't eternal. Over time, as the supply of nearby matter dwindles, these black holes enter a quieter phase, becoming less active but still lurking at the centers of galaxies. Even in this dormant state, supermassive black holes continue to exert their influence. They can reignite when galaxies collide, merging with other black holes or consuming new material. These events can trigger bursts of energy and reshape their surroundings once again. But what happens to these black holes in the distant future? According to Stephen Hawking's theory of Hawking radiation, black holes can slowly lose mass by emitting radiation, a process that takes an unimaginably long time. While the full life cycle of supermassive black holes remains a topic of ongoing research, understanding their stages helps us piece together their role in the cosmos. From their dramatic beginnings to their potential fade into the void, these objects remind us of the dynamic and ever-changing nature of the universe. Next, we'll explore how supermassive black holes shape the fate of galaxies during cosmic collisions, a process that marks another chapter in their extraordinary existence. Now, let's turn our attention to one of the most spectacular and destructive events in the cosmos, galactic collisions. When galaxies collide, their supermassive black holes take center stage in a dramatic cosmic dance. These collisions are not rare, they're a fundamental part of how the universe evolves. Imagine two galaxies, each with its own supermassive black hole at the center, slowly spiraling toward each other over millions of years. As they draw closer, the immense gravitational forces begin to pull them together, setting the stage for an extraordinary encounter. Initially, the black holes orbit each other, creating ripples in space-time known as gravitational waves. These waves carry energy away from the system, causing the black holes to spiral closer and closer. Eventually, they merge into a single, more massive black hole, releasing an enormous burst of energy in the process. This merger can be one of the most powerful events in the universe, outshining entire galaxies for a brief moment. But the impact of these collisions goes far beyond the black holes themselves. As galaxies merge, their gas and dust are disrupted, leading to intense bursts of star formation. New stars are born in dazzling displays, while others are flung out into intergalactic space. The supermassive black holes, now merged, continue to influence their new host galaxy, shaping its structure and evolution. These galactic collisions also have long-term consequences. The merged black hole can reignite as a quasar, feeding on the abundant gas and dust stirred up by the collision. This can trigger powerful jets of particles which travel at nearly the speed of light and impact the surrounding environment. In some cases, these jets can heat up gas in the galaxy, preventing it from cooling and forming new stars. Galactic collisions remind us of the dynamic and interconnected nature of the universe. They are not just destructive events, but also opportunities for renewal and transformation. Next, we'll explore the origins of the very first black holes in the universe, shedding light on how these cosmic giants came to dominate the centers of galaxies. Shifting our gaze back in time, we arrive at the dawn of the universe, where the first supermassive black holes began to take shape. These cosmic giants didn't form in the way we might expect. In fact, their origins are tied to the chaotic and rapidly evolving environment of the early universe, just a few 100 million years after the Big Bang. During this period, the universe was a vastly different place. It was smaller, denser, and filled with clouds of gas and dark matter. Within these clouds, the seeds of the first black holes were sown. One leading theory suggests that these seeds formed through the direct collapse of massive gas clouds. Unlike the black holes we see today, which often form from the remnants of dying stars, these early black holes were born directly from the collapse of these enormous clouds, bypassing the stellar stage entirely. These primordial black holes grew at an astonishing rate. In the dense and turbulent environment of the early universe, they had access to an abundance of gas and matter to feed on. As they consumed this material, their masses ballooned, eventually reaching supermassive proportions. Some scientists believe that these early black holes could have grown to billions of times the mass of our Sun within just a few 100 million years. The formation of these first supermassive black holes had a profound impact on the cosmos. They became the anchors around which the first galaxies formed. Their immense gravitational pull gathered gas and dark matter, setting the stage for the birth of stars and the creation of galactic structures. Over time, these black holes shaped the evolution of galaxies, influencing their growth and behavior in ways we're still working to understand. Interestingly, the first supermassive black holes also played a role in the reionization of the universe. As they fed on matter, they emitted vast amounts of energy in the form of radiation. This radiation helped ionize the neutral hydrogen that filled the early universe, turning it into the transparent cosmos we see today. Without these black holes, the universe might have remained a dark and opaque place. The study of the first black holes offers us a window into the early universe and the processes that shaped it. By understanding how they formed and grew, we can uncover clues about the origins of galaxies, the distribution of matter, and the timeline of cosmic evolution. As we continue to explore these ancient giants, we're reminded just how interconnected the story of the universe truly is. Now, let's turn our attention to another fascinating aspect of supermassive black holes, their influence on the formation of new stars. This interplay between destruction and creation reveals yet another layer of their complexity. Delving deeper into the cosmic dance of supermassive black holes, we uncover their dual role in the process of star formation. These behemoths, often seen as agents of destruction, also hold the power to both ignite and stifle the birth of new stars within their galaxies. Let's explore how this delicate balance plays out. When a supermassive black hole is actively feeding, it can unleash tremendous amounts of energy in the form of radiation and powerful jets of particles. These jets, traveling at nearly the speed of light, can heat up the surrounding gas in the galaxy. When this happens, the gas becomes too hot and turbulent to collapse under its own gravity, effectively putting a halt to star formation. This phenomenon is often referred to as quenching, and it's one way supermassive black holes can suppress the creation of new stars. However, the story doesn't end there. Supermassive black holes can also play a role in triggering star formation under the right conditions. When the jets and outflows from a black hole interact with dense clouds of gas, they can compress the material, creating regions where stars begin to form. This process is somewhat like a cosmic snowplow, where the energy from the black hole pushes gas together, setting the stage for new stellar births. Additionally, the gravitational influence of a supermassive black hole can shape the structure of its host galaxy. As it pulls matter toward its center, it can create zones of higher density where star formation becomes more likely. In some cases, the collision of galaxies triggering the merger of their supermassive black holes can also lead to bursts of star formation as the gravitational forces stir up and compress gas clouds. This dual role of supermassive black holes highlights their complexity and the intricate ways they interact with their surroundings. They're not just cosmic vacuums, they're dynamic forces that can both nurture and hinder the birth of stars, shaping the evolution of galaxies over billions of years. Next, we'll explore another intriguing aspect of these cosmic giants, their potential connection to the mysterious force known as dark energy. How might supermassive black holes be influencing the very fabric of the universe itself? Now, let's turn our attention to one of the most profound mysteries in cosmology, the connection between supermassive black holes and dark energy. Dark energy, the enigmatic force driving the accelerated expansion of the universe, has puzzled scientists for decades. Could supermassive black holes, these titans of gravity, hold clues to understanding this cosmic puzzle? One intriguing hypothesis suggests that supermassive black holes might play a role in the behavior of dark energy. While black holes are known for their immense gravitational pull, some theories propose that they could also be linked to the mechanisms driving the universe's expansion. This idea stems from the observation that the growth of supermassive black holes over cosmic time seems to align with the rate of the universe's expansion. Could there be a hidden connection? Scientists speculate that the energy released by supermassive black holes through processes like accretion and the emission of jets might interact with the fabric of spacetime itself. This interaction could influence the properties of dark energy, subtly shaping the way the universe expands. Additionally, the sheer mass of supermassive black holes, concentrated in such small regions, might create localized effects on spacetime that contribute to the overall dynamics of cosmic expansion. Another angle considers the role of black holes in the cosmic web, the vast network of galaxies and dark matter that structures the universe. As supermassive black holes evolve and interact with their surroundings, they might influence the distribution of dark energy on a larger scale. This could explain why the expansion of the universe appears to accelerate in certain regions more than others. While these ideas remain speculative, they open up exciting avenues for research. Understanding the relationship between supermassive black holes and dark energy could revolutionize our knowledge of the universe's fundamental forces. It's a reminder that even the most mysterious aspects of the cosmos might be interconnected in ways we're only beginning to explore. Next, we'll delve into another fascinating phenomenon, the role of quasars in regulating star formation, and how supermassive black holes use these luminous beacons to shape their galaxies. Shifting our focus to the dynamic interplay between supermassive black holes and their surroundings, let's explore the fascinating concept of quasar feedback. Quasars, the brightest objects in the universe, are powered by supermassive black holes actively consuming vast amounts of matter. But their influence extends far beyond their dazzling light. These cosmic beacons play a critical role in shaping the evolution of their host galaxies. At the heart of this process is the ability of quasars to heat and expel gas, a mechanism known as quasar feedback. As supermassive black holes devour surrounding material, they release enormous amounts of energy, much of which radiates outward as intense light and heat. This energy can heat up the surrounding gas to such extreme temperatures that it is pushed out of the galaxy, creating powerful outflows. These outflows have a profound impact on star formation. Gas is the raw material from which stars are born, so when it is expelled, star formation can be significantly slowed or even halted. This might sound counterintuitive, but it's a crucial way supermassive black holes regulate their galaxies. Without this feedback, galaxies might grow too quickly, exhausting their gas supplies and leading to an unsustainable burst of star formation. Quasar feedback also helps explain why some galaxies appear to turn off their star formation. As the supermassive black hole at the galaxy's center becomes active, it heats and expels gas, effectively quenching the birth of new stars. This process creates a delicate balance, ensuring that galaxies don't burn through their resources too quickly. Additionally, these outflows can carry heavy elements forged in the hearts of stars out into the intergalactic medium. This enriches the space between galaxies, providing the building blocks for future generations of stars and planets. Quasar feedback is a testament to the interconnectedness of cosmic processes. Supermassive black holes, while often seen as destructive forces, play a vital role in sculpting their galaxies and maintaining the delicate equilibrium of the universe. By regulating star formation and redistributing matter, they ensure that galaxies evolve in a sustainable and balanced way. Next, we'll uncover another intriguing mystery: the puzzling absence of supermassive black holes in some galaxies, and what this might tell us about their formation and evolution. Now let's turn our attention to a curious cosmic puzzle, the mystery of missing supermassive black holes. While we've come to expect these colossal objects at the centers of most galaxies, some galaxies appear to be without them. This absence raises intriguing questions about their formation and evolution. One possible explanation for this anomaly lies in the unique history of these galaxies. Some may have never hosted a supermassive black hole to begin with. This could happen if the galaxy formed in an environment where the conditions necessary for a black hole's growth were never met. For instance, if the galaxy lacked the dense gas or stellar material needed for a black hole to form or grow, it might remain devoid of one. Another theory suggests that these galaxies could have once had supermassive black holes, but they were ejected due to dramatic cosmic events. When galaxies collide, their central black holes can merge, releasing immense gravitational waves. In some cases, this collision might propel the newly formed black hole out of the galaxy entirely, leaving it behind as a wandering object in intergalactic space. Alternatively, the missing black holes might simply be hiding. Some supermassive black holes could be dormant with little to no activity, making them incredibly difficult to detect. Without the telltale signs of glowing accretion disks or energetic jets, they might remain invisible to our telescopes. There's also the possibility that these galaxies are in a transitional phase. Perhaps their black holes are still in the early stages of formation, too small or faint to be observed with current technology. Over time, as they accumulate more mass, they could become detectable. The absence of supermassive black holes in certain galaxies challenges our understanding of how these cosmic giants form and evolve. It opens up new avenues for research, encouraging scientists to explore the diverse conditions that shape galaxies and the black holes at their hearts. Next, we'll delve into another fascinating phenomenon: the role of supermassive black holes in producing high-energy cosmic rays. Shifting our focus to another cosmic marvel, let's explore how supermassive black holes play a significant role in the creation of high-energy cosmic rays. These rays are some of the most energetic particles in the universe, traveling at nearly the speed of light, and their origins have long been a subject of intense scientific curiosity. Supermassive black holes, with their immense gravitational forces and dynamic environments, are now understood to be key players in this phenomenon. At the heart of this process lies the powerful jets of particles that supermassive black holes often eject into space. These jets, composed of charged particles like protons and electrons, are accelerated to incredible speeds by the black hole's magnetic fields and intense gravity. As these particles travel outward, they collide with other matter in their path, creating a cascade of secondary particles. Some of these particles are flung into the vastness of intergalactic space, becoming the high-energy cosmic rays we detect on Earth. The environments around supermassive black holes are ideal for this kind of particle acceleration. The accretion disk, a swirling ring of gas and dust surrounding the black hole, generates immense heat and magnetic fields. These conditions act like a natural particle accelerator, boosting the energy of particles to extreme levels. Additionally, the shock waves produced by the jets can further energize particles, propelling them to even higher velocities. What makes cosmic rays so fascinating is their ability to travel across vast distances, carrying information about their origins. By studying these rays, scientists can learn more about the processes occurring near supermassive black holes and the environments that produce them. This research not only deepens our understanding of black holes, but also sheds light on the broader mechanisms of particle acceleration in the universe. Supermassive black holes, with their ability to generate such high-energy phenomena, continue to reveal new aspects of their immense power and influence. As we uncover more about their role in producing cosmic rays, we gain valuable insights into the cosmic processes that shape our universe. Next, we'll examine another dynamic aspect of these cosmic giants, the powerful galactic outflows they create, which can reshape entire galaxies. Moving deeper into the cosmic realm, let's uncover another astonishing phenomenon, the galactic outflows driven by supermassive black holes. These outflows are massive streams of gas and particles that surge outward from the centers of galaxies, propelled by the immense energy of the black holes themselves. They are not just spectacular to observe, but also play a critical role in shaping the structure and evolution of galaxies. These outflows are often triggered by the intense activity around the supermassive black hole, particularly from its accretion disk and jets. As matter spirals into the black hole, it releases enormous amounts of energy in the form of radiation and magnetic fields. This energy can heat up the surrounding gas, causing it to expand and burst outward into space. In some cases, the jets ejected by the black hole push gas and dust along with them, creating vast streams that can extend far beyond the galaxy itself. One of the most remarkable effects of these outflows is their ability to regulate star formation. When the outflowing gas is pushed outward, it can sweep away the raw materials needed to form new stars, effectively slowing down or even halting star formation in certain regions of the galaxy. This process, known as quenching, helps explain why some galaxies transition from being star-forming powerhouses to quiet, aging systems. Galactic outflows also play a role in distributing elements throughout the universe. The gas ejected from these outflows carries with it heavy elements like carbon, oxygen, and iron, which are forged in the hearts of stars. As these elements travel through space, they can eventually become part of new galaxies or star-forming regions, enriching the cosmic environment with the building blocks of life. In addition to their impact on star formation and chemical distribution, these outflows also influence the structure of the intergalactic medium, the vast diffuse gas that fills the space between galaxies. By injecting energy and matter into this medium, galactic outflows help shape the large-scale structure of the universe, contributing to the intricate cosmic web that connects galaxies across billions of light-years. Supermassive black holes, through their ability to generate these powerful outflows, act as cosmic sculptors, molding the evolution of galaxies and the universe at large. Their influence extends far beyond their event horizons, leaving an indelible mark on the cosmos. Next, we'll turn our attention to the dynamic activity in the cores of galaxies, where supermassive black holes power some of the most intense phenomena in the universe, active galactic nuclei. Now, let's dive into the bustling cores of galaxies, where supermassive black holes unleash some of the most energetic phenomena in the cosmos, active galactic nuclei. At the heart of many galaxies lies a supermassive black hole surrounded by a swirling accretion disk of gas and dust. When this material spirals toward the black hole, it doesn't go quietly. It releases staggering amounts of energy, lighting up the galactic center in a way that can outshine the entire galaxy. This glowing core is what astronomers call an active galactic nucleus, or AGN for short. Active galactic nuclei come in several varieties, each with its own unique characteristics. The most well-known type is the quasar, which shines so brightly that it can be seen from billions of light-years away. Quasars are powered by supermassive black holes that are actively feeding, gobbling up vast amounts of matter and radiating immense energy across the electromagnetic spectrum. Another type is the Seyfert galaxy, which features a bright nucleus but is less luminous than a quasar. Seyfert galaxies often show strong emissions in specific wavelengths, such as X-rays or infrared, revealing the intense activity around their central black holes. Then there are radio galaxies, which are distinguished by their powerful jets of particles that shoot out from the black hole at nearly the speed of light. These jets can stretch for millions of light-years, creating enormous lobes of radio emissions that dominate the galaxy's appearance. At the other end of the spectrum are blazars, a type of AGN where the jets are pointed almost directly at Earth, making them appear exceptionally bright and variable. The energy emitted by active galactic nuclei doesn't just light up the cosmos, it also shapes the galaxy around it. The intense radiation can heat up surrounding gas, preventing it from cooling and forming new stars. In some cases, AGN can even trigger star formation by compressing gas clouds with their powerful outflows. This dual role, both suppressing and encouraging star formation, highlights the complex relationship between supermassive black holes and their host galaxies. Active galactic nuclei also serve as cosmic laboratories, allowing scientists to study the extreme physics at work near supermassive black holes. By observing the light emitted by AGN, astronomers can measure the black hole's mass, spin, and the properties of its accretion disk. These observations provide crucial insights into how supermassive black holes grow and evolve over time. The study of active galactic nuclei not only deepens our understanding of black holes, but also sheds light on the broader processes that shape galaxies and the universe itself. As we continue to explore these luminous cores, we uncover more secrets about the forces that drive the cosmos. Next, we'll explore one of the most explosive events linked to supermassive black holes, gamma-ray bursts, where the universe unleashes unimaginable energy in a matter of seconds. Shifting our focus to one of the most violent displays of cosmic power, let's delve into the connection between supermassive black holes and gamma-ray bursts. These bursts are among the most energetic events in the universe, releasing in mere seconds more energy than our Sun will emit in its entire lifetime. While many gamma-ray bursts are associated with the collapse of massive stars or the merger of neutron stars, supermassive black holes may also play a role in some of these extraordinary explosions. One possible link involves the jets produced by supermassive black holes. As matter spirals into a black hole, it can form incredibly powerful jets that shoot out along its rotational axis at nearly the speed of light. In some cases, these jets might generate gamma-ray bursts if they collide with surrounding material or if their internal structure leads to intense shock waves. The energy released in these interactions can produce a short-lived but incredibly bright flash of gamma rays, detectable across vast cosmic distances. Another scenario involves the tidal disruption of stars. When a star wanders too close to a supermassive black hole, the immense gravitational forces can tear it apart in a process known as a tidal disruption event. As the star's debris falls into the black hole, it can ignite a temporary burst of gamma rays, especially if the black hole is actively feeding and producing jets. These events, though rare, offer a fascinating glimpse into the extreme physics at play near supermassive black holes. Gamma-ray bursts also provide valuable insights into the early universe. Because they are so bright, they can be detected from billions of light years away, acting as cosmic beacons that illuminate the distant cosmos. By studying their properties, scientists can learn about the conditions in the early universe and the role supermassive black holes might have played in shaping it. These bursts are not just spectacular cosmic fireworks, they are also powerful tools for understanding the universe. They help us probe the behavior of matter under extreme conditions, the formation of supermassive black holes, and the evolution of galaxies. As we continue to unravel the mysteries of gamma-ray bursts, we gain a deeper appreciation for the profound influence of supermassive black holes on the cosmos. Now, let's turn our attention to another dramatic phenomenon linked to supermassive black holes: the tidal disruption events that occur when stars get too close to these gravitational giants. Building on the incredible power of supermassive black holes, let's explore what happens when a star dares to venture too close to these gravitational titans. When a star approaches a supermassive black hole, it doesn't stand a chance. The immense tidal forces, the difference in gravitational pull between the star's near and far sides, stretch and distort it in a process known as spaghettification. Imagine pulling on a piece of taffy until it becomes a long, thin strand. That's essentially what happens to the star as it's torn apart by the black hole's overwhelming gravity. As the star is ripped apart, its material forms a swirling disk around the black hole, known as an accretion disk. This disk glows brightly as the star's debris heats up through friction and gravitational energy. In some cases, the black hole can launch powerful jets of particles and radiation from its poles, adding to the spectacle. The entire event can shine brighter than an entire galaxy for weeks or even months, making it one of the most dramatic displays in the universe. Tidal disruption events are more than just cosmic fireworks. They provide a unique opportunity for scientists to study the behavior of matter under extreme conditions. By observing these events, researchers can learn about the properties of supermassive black holes, such as their mass and spin. They also offer insights into how black holes grow by feeding on stars and other cosmic material. These events are rare, occurring roughly once every 10,000 years in a typical galaxy. But when they do happen, they leave an unmistakable signature. Telescopes across the electromagnetic spectrum, from X-rays to radio waves, can detect the bright flashes and lingering afterglow of these stellar disruptions. By analyzing this light, astronomers can piece together the sequence of events and the physics at play. Tidal disruption events also have broader implications for our understanding of the universe. They reveal how supermassive black holes interact with their surroundings and influence the evolution of their host galaxies. These violent encounters remind us of the immense power of black holes and their pivotal role in shaping the cosmos. Now, let's turn our attention to another remarkable phenomenon: how supermassive black holes might have contributed to the reionization of the early universe. Now, let's journey back in time to one of the most transformative periods in cosmic history, the era of reionization. This pivotal phase occurred when the first stars and galaxies began to illuminate the early universe, but there's growing evidence that supermassive black holes played a crucial role in this process. As these black holes fed on surrounding gas and dust, they unleashed torrents of radiation and powerful jets of particles. This energy likely helped ionize the vast clouds of hydrogen that filled the universe, breaking them apart into free protons and electrons. The role of supermassive black holes in cosmic reionization is complex and fascinating. Their intense radiation could have traveled vast distances, reaching even the most remote corners of the universe. This energy would have heated and ionized the hydrogen gas, creating the conditions necessary for light to travel freely. Without this process, the universe would have remained shrouded in a fog of neutral hydrogen, obscuring the earliest galaxies and stars from our view. But how did these supermassive black holes form so early in the universe's history? Some theories suggest they grew rapidly from seed black holes, perhaps remnants of the first massive stars, or formed through the direct collapse of dense gas clouds. Once established, their voracious appetite for matter allowed them to grow quickly, becoming the powerful engines of reionization. The light from quasars, powered by supermassive black holes, provides direct evidence of their role in this cosmic transformation. These incredibly bright objects, observed at immense distances, act as beacons from the early universe. Their spectra reveal the state of the intergalactic medium, showing how it gradually became ionized over time. This data helps astronomers piece together the timeline and mechanisms of reionization. While stars and galaxies played a significant part in this process, supermassive black holes likely provided the extra boost needed to complete it. Their ability to produce immense amounts of energy in a relatively short time made them key players in shaping the universe as we see it today. Without their influence, the cosmos might have remained dark and opaque for much longer, delaying the formation of the first galaxies and ultimately the rise of complex structures like our own Milky Way. This connection between supermassive black holes and cosmic reionization highlights their profound impact on the universe's evolution. As we uncover more about these enigmatic objects, we gain a deeper understanding of how they helped transform the cosmos from a dark, murky expanse into the vibrant, illuminated universe we observe today. Shifting our focus to the more dramatic side of cosmic events, let's explore a process that sounds like it belongs in a science fiction story: galactic cannibalism. At the centers of many galaxies, supermassive black holes aren't just passively sitting there. They're actively growing by devouring anything that comes too close, including smaller black holes and stars. This process is a key factor in how these cosmic giants reach their staggering sizes. When galaxies collide or come close together, their supermassive black holes can interact in a spectacular display of gravitational forces. As the galaxies merge, stars, gas, and even smaller black holes are pulled toward the central black hole of the larger galaxy. This material spirals inward, eventually crossing the event horizon where it's added to the black hole's mass. It's a cosmic feeding frenzy on an unimaginable scale. But what happens when two supermassive black holes meet? In some cases, they can orbit each other, forming a binary system. Over time, their orbits decay due to the emission of gravitational waves, and they eventually merge into one even larger black hole. These mergers release an enormous amount of energy, creating ripples in spacetime that we can detect as gravitational waves. This process is one of the most violent and energetic events in the universe. Stars that wander too close to a supermassive black hole face a grim fate. The black hole's immense gravitational pull can tear the star apart in a process called a tidal disruption event. The star's debris is then pulled into the black hole, fueling its growth and producing bursts of radiation that can be observed from vast distances. This phenomenon of galactic cannibalism isn't just fascinating, it's essential to understanding how supermassive black holes evolve. By consuming stars and smaller black holes, these cosmic giants can grow to millions or even billions of times the mass of our Sun. Their growth, in turn, influences the structure and evolution of their host galaxies, creating a dynamic interplay between the black hole and its surroundings. In the grand tapestry of the universe, galactic cannibalism is a reminder of the raw power and scale of supermassive black holes. As we continue to study these events, we uncover more about the processes that shape galaxies and the universe itself. And with that, we move closer to understanding the full story of these enigmatic cosmic engines. Now, let's turn our gaze toward the far future and consider the profound role supermassive black holes might play in the ultimate fate of the universe. These cosmic giants lurking at the hearts of galaxies aren't just passive observers, they could be key players in shaping how the universe evolves over unimaginable timescales. One of the most intriguing possibilities is the connection between supermassive black holes and the expansion of the universe. Scientists have long been puzzled by dark energy, the mysterious force driving the accelerated expansion of the cosmos. Some theories suggest that supermassive black holes might interact with this cosmic force in ways we don't yet fully understand. Could they be influencing or even contributing to the behavior of dark energy? The answer to this question could reshape our understanding of the universe's destiny. As the universe continues to expand, galaxies will grow farther apart, and the era of star formation will eventually come to an end. In this distant future, supermassive black holes may become the dominant structures in the cosmos. With no new stars forming, these black holes will continue to grow by consuming the remnants of stars, gas, and even other black holes. Over trillions of years, they could become the last remaining sources of energy in an increasingly dark and empty universe. But what happens beyond that? Some scientists speculate that supermassive black holes could eventually evaporate through a process known as Hawking radiation. This phenomenon, predicted by Stephen Hawking, suggests that black holes slowly lose mass over time, emitting particles until they eventually vanish. If this process is accurate, it could mean that supermassive black holes, once thought to be eternal, might have a finite lifespan. Their evaporation could mark the final chapter in the life cycle of the universe itself. However, the story doesn't end there. The evaporation of supermassive black holes could release vast amounts of energy, potentially reigniting the cosmos in a burst of activity, even if only for a fleeting moment. This cycle of growth, evaporation, and renewal could hint at a universe that undergoes endless transformations, with supermassive black holes at its center. While these ideas remain speculative, they highlight the profound influence these cosmic giants might have on the universe's ultimate destiny. From shaping the expansion of space to potentially marking its final moments, supermassive black holes are more than just gravitational behemoths. They could be the architects of the cosmos's far future. As we continue to unravel their mysteries, we edge closer to understanding not just the universe as it is, but as it will be, billions or even trillions of years from now. Shifting our focus to an even more mind-bending idea, let's explore the concept of supermassive black holes as potential time machines. This might sound like science fiction, but it's a topic that physicists take seriously, thanks to the strange properties of these cosmic giants. At the heart of this idea lies the way black holes warp the fabric of spacetime itself. Einstein's theory of general relativity tells us that massive objects like supermassive black holes can bend spacetime so severely that time itself is affected. Near the event horizon of a black hole, time slows down dramatically due to the immense gravitational pull. This phenomenon, known as time dilation, means that a clock near a black hole would tick much slower compared to one far away from it. But what if we could harness this effect to travel through time? Some theories suggest that under extreme conditions, black holes might create closed time-like curves, paths through spacetime that loop back on themselves. In simpler terms, these could act like cosmic shortcuts, allowing an object or even a person to travel back to their own past. One of the most famous proposed methods involves a supermassive black hole surrounded by a rapidly spinning accretion disk. The intense rotation could twist spacetime enough to create these closed loops. However, the practical challenges are immense. For one, the gravitational forces near a black hole are so extreme that they would tear apart anything trying to approach. Additionally, the energy and technology required to navigate such a journey are far beyond anything we can imagine today. Despite these hurdles, the idea of using supermassive black holes as time machines continues to captivate scientists and science enthusiasts alike. It pushes the boundaries of our understanding of physics and challenges us to think about the universe in entirely new ways. While this remains speculative, it's a reminder that the mysteries of supermassive black holes are as vast and complex as the universe itself. As we ponder these possibilities, we're not just exploring black holes, we're reimagining the very nature of time and space. Who knows? The secrets of time travel might just be hiding in the shadows of these cosmic titans, waiting for future discoveries to unlock their potential. Now, let's turn our attention to a fascinating question. Could supermassive black holes hold clues to the search for extraterrestrial life? While these cosmic giants are often seen as destructive forces, they might also play a surprising role in shaping the conditions necessary for life in the universe. One key factor lies in their influence on their host galaxies. Supermassive black holes, particularly those in active galactic nuclei, can heat up surrounding gas and drive powerful outflows. These outflows can clear away material, preventing the formation of new stars. While this might seem counterintuitive, it could actually create stable environments where life has a better chance to thrive. For instance, in galaxies where star formation is regulated, there's less risk of nearby supernova, whose intense radiation could be harmful to developing life. On the other hand, the energy emitted by supermassive black holes can also trigger star formation in certain regions, potentially creating habitable zones. Stars formed in these areas might host planets with the right conditions for life. Additionally, the intense radiation and magnetic fields around black holes could contribute to the complex chemistry needed to form organic molecules, the building blocks of life. But what about the search for intelligent life? Some theories suggest that advanced civilizations might harness the immense energy of supermassive black holes. If aliens exist, they could be drawn to these cosmic powerhouses, either to study them or to use their energy for technological purposes. This makes supermassive black holes intriguing targets in the hunt for extraterrestrial intelligence. Interestingly, the presence of a supermassive black hole might also signal a galaxy's potential to host life. Galaxies with these black holes tend to be more massive and stable, providing long-term environments where life could evolve over billions of years. While the connection between supermassive black holes and extraterrestrial life is still speculative, it opens up exciting avenues for exploration. By studying these mysterious objects, we might not only unravel the secrets of the cosmos, but also uncover clues to one of humanity's biggest questions: are we alone in the universe? As we continue our cosmic journey, let's dive into another intriguing secret: how supermassive black holes might fit into the multiverse theory, where multiple universes could exist. Now, let's venture into one of the most mind-bending ideas in modern physics, the multiverse theory, and explore how supermassive black holes might fit into this cosmic puzzle. The multiverse theory suggests that our universe is just one of many, each with its own unique laws of physics and structure. But where do supermassive black holes come into play? One intriguing possibility is that supermassive black holes could act as gateways or bridges between these parallel universes. Some theories propose that the extreme conditions inside a black hole's singularity might create a wormhole, a theoretical tunnel through space-time that could connect different universes. While this remains speculative, it opens up fascinating questions about the role these cosmic giants might play in a multiverse framework. Another angle considers the idea that supermassive black holes could be remnants of other universes. According to certain models, when a universe collapses, it might leave behind a black hole that seeds the birth of a new universe. This cyclical process could mean that our universe itself was born from a black hole in another cosmos. Furthermore, the behavior of supermassive black holes might offer clues about the nature of the multiverse. For instance, their immense gravitational influence and ability to warp spacetime could provide insights into how multiple universes interact or remain separate. Studying these black holes could help scientists test the validity of multiverse theories and better understand the fabric of reality itself. While these ideas are still in the realm of speculation, they highlight the profound mysteries surrounding supermassive black holes and their potential role in a much larger cosmic story. Whether as gateways, cosmic remnants, or tools for understanding multiple universes, these enigmatic objects continue to stretch the boundaries of our imagination and scientific exploration. As we ponder these possibilities, we'll turn our attention to another captivating secret: the role supermassive black holes might have played in the Big Bang, the explosive event that gave birth to our universe. Turning our gaze back to the very beginning, let's explore a fascinating idea. Could supermassive black holes have played a role in the Big Bang itself? The Big Bang is often described as the explosive event that birthed our universe. But what if supermassive black holes were somehow involved in this cosmic genesis? One theory suggests that a supermassive black hole from a previous universe could have triggered the Big Bang. In this scenario, when a universe collapses, it might leave behind a black hole, a remnant so dense and powerful that it could seed the birth of a new universe. This idea ties into the concept of a cyclical universe, where the death of one cosmos gives rise to another. Another angle considers the extreme conditions inside a black hole's singularity. Scientists speculate that these conditions might resemble those of the early universe, hinting at a possible connection. Could the singularity of a supermassive black hole be the birthplace of a new cosmic explosion? While this remains speculative, it's a thought-provoking idea that challenges our understanding of both black holes and the Big Bang. Moreover, the immense gravitational forces of supermassive black holes might have influenced the distribution of matter and energy during the universe's earliest moments. Their presence could have shaped the initial conditions of the Big Bang, setting the stage for the formation of galaxies, stars, and planets. Though these ideas are still in the realm of theory, they invite us to consider supermassive black holes not just as cosmic destroyers, but as potential creators, an entirely new perspective on their role in the grand tapestry of the universe. As we continue to unravel these mysteries, we'll now shift our focus to another intriguing secret: the holographic principle, and how supermassive black holes might support this revolutionary theory. Now, let's venture into a mind-bending concept that might just reshape how we understand reality itself: the holographic principle. Imagine if everything we perceive in our three-dimensional universe could actually be encoded on a two-dimensional surface like a cosmic hologram. Intriguingly, supermassive black holes might hold the key to unlocking this revolutionary idea. At the heart of the holographic principle is the idea that the information about everything within a region of space can be represented on its boundary. Think of it like a movie projected onto a screen. What we see as a three-dimensional universe could be a projection from a two-dimensional surface. Supermassive black holes, with their immense gravitational pull and event horizons, provide a unique testing ground for this theory. The event horizon of a black hole, the point of no return, acts as a boundary that captures and encodes information about anything that falls into it. According to the holographic principle, all the information about the object swallowed by the black hole is preserved on its surface, not lost forever. This challenges the classic notion that information is destroyed in black holes, a problem known as the black hole information paradox. Moreover, the area of a black hole's event horizon is proportional to its entropy, a measure of disorder or information content. This connection suggests that the surface of a black hole could store vast amounts of information, much like a holographic plate. If this is true for black holes, it raises the possibility that our entire universe might operate in a similar way, a holographic projection of information stored on its cosmic boundary. While this idea remains speculative, it opens up a fascinating dialogue between quantum mechanics and gravity, two of the most fundamental yet incompatible theories in physics. Supermassive black holes, with their extreme properties, might just be the bridge we need to explore this deeper truth about the nature of reality. As we continue to unravel these mysteries, we'll now shift our focus to another captivating secret: the connection between supermassive black holes and cosmic inflation, a period of rapid expansion in the early universe. As we turn our attention to the early moments of the universe, another intriguing mystery comes into focus: the role supermassive black holes might have played during cosmic inflation. This period of rapid expansion, which occurred just fractions of a second after the Big Bang, set the stage for the universe as we know it today. Interestingly, supermassive black holes could hold clues to understanding this transformative phase. One theory suggests that the immense gravitational forces within supermassive black holes might have influenced the dynamics of cosmic inflation. During this brief but explosive period, space itself expanded faster than the speed of light, stretching the fabric of the universe and seeding the structures we see today. The energy densities involved were unimaginably high, and some researchers propose that supermassive black holes, with their extreme conditions, could have acted as focal points for this expansion. Another angle explores the possibility that supermassive black holes formed much earlier than previously thought, perhaps even during or shortly after inflation. If true, these black holes would have interacted with the rapidly expanding universe in ways that left imprints on its large-scale structure. The distribution of galaxies and cosmic voids we observe today might carry traces of these ancient interactions. Additionally, the gravitational waves generated by supermassive black holes could provide a window into this early epoch. These ripples in spacetime, produced by black hole mergers or other violent events, might carry information about the conditions of the universe during inflation. By studying these waves, scientists hope to piece together how supermassive black holes could have shaped the cosmos in its infancy. While the connection between supermassive black holes and cosmic inflation remains speculative, it opens up exciting avenues for research. These enigmatic objects, often seen as destroyers, might also hold the key to understanding the birth and evolution of the universe itself. Now, let's delve into another profound secret: the role supermassive black holes might play in the arrow of time, and how they could influence the very direction of causality in the cosmos. Shifting our focus to the nature of time itself, we uncover yet another fascinating secret: the role supermassive black holes might play in shaping the arrow of time. This concept, which describes the one-way direction of time from past to future, is deeply connected to the laws of thermodynamics and entropy. Surprisingly, supermassive black holes could hold clues to understanding why time flows the way it does. At the heart of this mystery is the second law of thermodynamics, which states that entropy, or disorder, always increases over time. Supermassive black holes, with their immense gravitational pull and ability to consume matter, are thought to contribute to the overall entropy of the universe. As matter falls into a black hole, it increases the entropy of the system, reinforcing the arrow of time. This means these cosmic giants might play a critical role in maintaining the forward flow of time on a universal scale. Another intriguing idea is how the extreme conditions near a black hole could distort our perception of time. Due to the intense gravitational field, time slows down significantly as you approach the event horizon, a phenomenon known as time dilation. For an outside observer watching an object fall toward a black hole, it would appear to slow down almost to a stop, while time for the object itself would seem to pass normally. This warping of time offers a unique perspective on how black holes influence the very fabric of spacetime. Some theories even suggest that supermassive black holes could serve as natural timekeepers for the universe. Their sheer size and gravitational influence might create a kind of cosmic clock, aligning the flow of time across vast distances. This could help explain why the arrow of time appears consistent throughout the cosmos, even as the universe continues to expand and evolve. The connection between supermassive black holes and the arrow of time remains a topic of active research and debate. However, it's clear that these enigmatic objects have far-reaching implications for our understanding of time, causality, and the fundamental laws that govern the universe. Now, let's explore another captivating secret: how supermassive black holes might be linked to the strange phenomenon of quantum entanglement, and what this could mean for our understanding of reality. Turning our attention to the quantum realm, we uncover a startling possibility: supermassive black holes might hold the key to understanding one of the most perplexing phenomena in physics: quantum entanglement. Quantum entanglement occurs when two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This strange connection defies our classical understanding of space and time, and supermassive black holes could be at the heart of unraveling this mystery. One theory suggests that the immense gravitational fields of supermassive black holes might create conditions where quantum entanglement becomes amplified or even preserved. Inside a black hole, where the laws of physics as we know them break down, entangled particles could behave in ways that are impossible to observe anywhere else in the universe. This raises the question: could black holes serve as cosmic laboratories for studying the limits of quantum mechanics? Additionally, some researchers propose that the event horizon of a black hole might play a unique role in entanglement. When a particle falls into a black hole, its entangled partner outside the event horizon could retain information about the fallen particle. This idea has led to the development of theories like the holographic principle, which suggests that all the information about what falls into a black hole is encoded on its surface. This could mean that entanglement is not just a quantum quirk, but a fundamental feature of how the universe stores and processes information. Another intriguing possibility is that supermassive black holes might themselves be entangled with other black holes across the universe. If this is the case, it could provide a new framework for understanding the large-scale structure of the cosmos. Entangled black holes could form a network that connects distant regions of space, acting as bridges for information to travel instantaneously, something that would revolutionize our understanding of physics. The connection between supermassive black holes and quantum entanglement is still in its early stages of exploration, but it's clear that these cosmic giants could shed light on some of the deepest mysteries of the universe. By studying their interactions with the quantum world, we might finally begin to piece together how the smallest and largest scales of reality are intertwined. Now, let's move on to another fascinating idea: the speculative notion that supermassive black holes could be evidence that we live in a simulated universe, and what this means for our understanding of reality. Now, let's dive into a truly mind-bending idea: the simulation hypothesis, and how supermassive black holes might play a role in this speculative theory. Imagine for a moment that our universe is not the base reality but a highly advanced simulation, much like a cosmic video game. If this were true, supermassive black holes could hold clues to uncovering the truth. These enigmatic objects, with their extreme gravitational forces and ability to warp spacetime, might function as glitches or markers in the code of this simulated reality. One of the key arguments supporting the simulation hypothesis is the idea that our universe operates under mathematical laws, almost as if it were programmed. Supermassive black holes, with their precise and predictable behaviors governed by equations, could be seen as evidence of this underlying code. Their event horizons, which act as information boundaries, might represent limits to the simulation's processing power. Just as a computer has a finite memory, the universe might rely on black holes to manage or store data in ways we're only beginning to understand. Another intriguing possibility is that black holes could serve as rendering points in the simulation. In a video game, only the part of the world that's currently visible to the player is rendered in detail, saving computational resources. Similarly, black holes might mark regions where the simulation prioritizes its calculations, ensuring that the rest of the universe runs smoothly. This could explain why these objects are so dense and why they seem to operate at the very edge of physical laws. Some theorists even suggest that the holographic principle, which states that all the information in a volume of space can be encoded on its boundary, supports the simulation hypothesis. If the universe is a simulation, then black holes could be the ultimate data storage devices, encoding information on their event horizons in a way that mirrors how a computer stores data on a hard drive. While the simulation hypothesis remains highly speculative, it's fascinating to consider how supermassive black holes might fit into this framework. These cosmic phenomena, already shrouded in mystery, could be the key to unlocking whether our reality is as real as we perceive it, or something far more extraordinary. As we ponder this intriguing idea, let's turn our attention to another profound question: how supermassive black holes might help physicists develop a unified theory of everything, bringing together the forces that govern the universe. As we venture deeper into the mysteries of supermassive black holes, let's explore their potential role in unlocking the universe's ultimate puzzle, a unified theory of everything. For decades, physicists have sought to reconcile the two great pillars of modern science: quantum mechanics, which governs the tiny world of particles, and general relativity, which describes the vast cosmos. Supermassive black holes sitting at the intersection of these two realms might hold the key to bridging this divide. At the heart of this quest is the singularity within a black hole. Here, the laws of physics as we know them break down, offering a unique opportunity to study the extreme conditions where quantum effects and gravity collide. Understanding what happens in this region could provide insights into how these fundamental forces operate together, a crucial step toward a unified theory. Another fascinating aspect is the holographic principle, which suggests that all the information about a volume of space can be encoded on its boundary like a cosmic hologram. Supermassive black holes, with their event horizons acting as information boundaries, might serve as real-world examples of this principle. By studying how information is stored and processed at these horizons, scientists could gain valuable clues about the nature of spacetime itself. Furthermore, the immense gravitational fields of supermassive black holes create extreme environments where exotic phenomena, such as Hawking radiation and quantum entanglement, can be studied. These phenomena offer glimpses into the quantum nature of gravity, a missing piece in the puzzle of a unified theory. While the journey toward a theory of everything is far from complete, supermassive black holes provide a unique laboratory for testing ideas and pushing the boundaries of our understanding. These cosmic giants, once thought to be mere destroyers of matter, might instead illuminate the deepest secrets of the universe. As we continue to unravel these mysteries, let's turn our attention to the final frontier, the challenges and possibilities of humans exploring or studying supermassive black holes up close. Now let's shift our gaze to a thrilling yet daunting prospect: what it would take for humans to explore or study supermassive black holes up close. The idea of venturing near these cosmic giants is both fascinating and fraught with challenges. For one, the immense gravitational pull of a supermassive black hole makes even approaching one a perilous journey. The closest supermassive black hole to Earth, Sagittarius A, lies roughly 26,000 light-years away, a distance that, with current technology, is impossible to traverse within a human lifetime. Even if we could overcome the vast distances, the extreme environment near a supermassive black hole presents a host of dangers. The intense tidal forces would stretch and compress anything that gets too close, a process known as spaghettification. Additionally, the intense radiation from the accretion disk and relativistic jets would pose significant health risks to any human explorers. Yet, the potential rewards of studying these objects up close are immense. By observing a supermassive black hole firsthand, we could gather unprecedented data on their structure, behavior, and the extreme physics at play. For instance, we might directly measure the effects of time dilation, where time slows down significantly near the event horizon. We could also study the dynamics of the accretion disk in detail, gaining insights into how matter behaves under such extreme conditions. Robotic probes could play a crucial role in this exploration, allowing us to study supermassive black holes without putting human lives at risk. These probes could be equipped with advanced sensors to measure gravitational waves, radiation, and other phenomena. They could also capture high-resolution images and data, providing a wealth of information to scientists on Earth. Another intriguing possibility is the use of gravitational lensing, a phenomenon where the immense gravity of a black hole bends light, magnifying distant objects behind it. By positioning a spacecraft at the right distance, we could use a supermassive black hole as a natural telescope, potentially observing distant galaxies or even the early universe with incredible clarity. While the challenges of exploring supermassive black holes up close are immense, the potential for discovery is equally great. These cosmic behemoths hold the keys to understanding some of the most profound mysteries of the universe, and the pursuit of studying them could drive technological advancements that benefit humanity in unforeseen ways. The dream of exploring a supermassive black hole may seem distant, but as our understanding and technology evolve, it becomes a tantalizing possibility for the future of space exploration. As we wrap up our journey through the 50 secrets of supermassive black holes at galactic centers, it's clear these cosmic giants are far more than just gravitational monstrosities. They are the architects of galaxies, the engines of the universe, and the gateways to some of the most profound mysteries in existence. From their formation billions of years ago to their ongoing influence on the cosmos, supermassive black holes challenge our understanding of space, time, and reality itself. We've explored how they shape the evolution of galaxies, power quasars, and even influence the large-scale structure of the universe through the cosmic web. We've delved into the mind-bending physics of event horizons, singularities, and the bizarre phenomenon of time dilation. We've marveled at their ability to warp space-time, produce gravitational waves, and potentially connect to other universes or dimensions. Yet, for all we've uncovered, supermassive black holes remain shrouded in mystery. Questions about their origins, their ultimate fate, and their role in the broader tapestry of the cosmos continue to inspire scientists and dreamers alike. They remind us that the universe is a place of infinite wonder, where every discovery leads to new questions and every mystery beckons us to explore further. As you reflect on these secrets, let them inspire you to look up at the night sky with fresh curiosity. Each star, each galaxy, and each supermassive black hole tells a story that we are only beginning to understand. The cosmos invites us to keep questioning, keep exploring, and keep unraveling its deepest enigmas. If you've enjoyed this journey through the mysteries of supermassive black holes, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss out on our cosmic explorations. Share your thoughts in the comments below. What fascinates you most about these cosmic giants? Thank you for joining us on this incredible adventure through the heart of galaxies and the secrets of supermassive black holes. Until next time, keep looking up, stay curious, and remember, the universe is waiting to reveal its next great mystery.